Alright guys, so let's kind of pick up where we left off. This is our second video on chapter 16. Okay, we're going to do a little bit more with the Dino Nomenclature. It's based on the position of the hydroxyl group on the chiral carbon farthest from the carbonyl group, which is the most oxidized portion of the molecule. We've already talked about this a little bit. So it's the OH that's on the last chiral carbon. If it's on the right, it is D. If it is on the left, it is L. Okay. If we draw D-glucose, okay, and the good news is you don't have to memorize any of these. We are going to talk about some of their differences in a little bit, but D-glucose would look something like this. Okay, we've got our CHO group. Okay, 1, 2, 3, 4 chiral carbons, and then we have a CH2OH group at the bottom. For glucose, we have HOH, then we have OH, usually it's written the other way, that's okay, H, we have an OHH, and then you'll notice that in this one, which is the furthest, right, chiral carbon from the aldehyde, the OH is on the right. Okay, so you always focus on the chiral carbon that's the farthest away from the aldehyde group. Okay. We can draw these like this in the Fischer Projection format, which is often called the open chain form. Okay, or we can also draw them as a Haworth, I'm not sure how you say that, projection. Okay. There are two types of this projection. Okay, we have the alpha form, where the OH group is down in our final structure, and we have the beta form, where the OH group is up in our structure. Okay, so you're always looking when you're determining if something is alpha or beta. Okay, you see that there's an oxygen here, there's an oxygen here, right? You're always looking at the OH that is connected to the first carbon off of that oxygen. So here, this is the OH we would focus on, it's alpha. And then here, this is the OH we would focus on, it's beta. I like to remember that because beta is a bee and birds fly in the sky. And alpha kind of looks like a little fish. I know that's weird, but fish swim in the ocean, so they're down below. Okay, so we're going to kind of run through how to turn this into the Haworth projections on the next couple of slides. Here we go. So we're going to first start just by talking about important monosaccharides. The main one is glucose. Okay, it is the most important sugar in the human body. The concentration of your glucose in the blood is critical to normal body function. Okay, this is where insulin and things sometimes have to come in because your body does not appropriately handle the sugar. Okay, so we're going to run through and kind of talk about how to draw glucose. Okay, glucose is an aldohexose. All right, and we are going to go through this structure here and exactly what is kind of taking place. We're going to do that in more detail on the next slide, but I wanted to just kind of point a couple of things out. When you number your carbons, and you're definitely going to want to do this for these, the first carbon is always the one that is, closest to, or that is the aldehyde, or the one that is closest to the ketone. Okay, so you'll notice in this picture that it's numbered 1, then 2, 3, 4, 5, and 6. Okay, and they kept the numbering system throughout the entire pictures there. All right, what ends up actually happening is the OH here. Okay, and you'll kind of see it, right, because it's on the 5th carbon, so that the OH I circled in both of those is exactly the same. As the structure kind of turns and moves, that OH is the closest, right, to the double bonded OC. So this O is going to end up being the one that interacts with the aldehyde, okay, which in turn leads to the production of either this or this, okay. So we're going to get into that in great detail shortly. Something that's important to kind of note always with these is from the Fischer projection. Okay, when we draw our rings and when we turn them into rings, anything that is on the right side of our Fischer projection is said to go below the ring, and I'll tell you what that means on the next slide. And then anything on the left is always found above the ring. Okay, so we're going to go through this in great detail so that you have an idea of how to do it. And then I've actually posted some extra practice on this for you guys online with answer keys in the extra practice section. All right, so let's move on to the next slide and go over this in detail. All right, we are going to kind of go through how this turns into this. Okay. Here we go. All right. And this is definitely going to be something I think we're going to probably have to talk about during Zoom as well. I would say it's the most complicated part of this particular chapter. Okay. So the first thing I want to do is I kind of want to label all my carbons here. So I'm going to go 1, 2, 3, 4, 5, and 6. Okay. Then what I'm going to do is I'm going to redraw this in a slightly different conformation. Okay. What ends up happening is this carbon here. Okay. The structure is going to kind of rotate a little bit so that this oxygen is as far as possible 100% away from that aldehyde. Okay, so when I rewrite it after it rotates, it looks like this. Okay, so on the bottom, all right, this CH2OH is actually going to shift to the left, and the H is going to shift to the right. Okay, and the O actually ends up kind of shifting to the bottom, I feel like. Is what's taking place. Okay, again, a little bit weird, but here we go. So if I draw things out, and I'm going to keep my carbons 1, 2, 3, 4, 5. Okay, I am going to shift that CH2OH that was on the bottom over here. Okay, so I'm shifting this over here like that. Right? I'm going to shift my H that was there here. Okay. And then in essence, my OH is down here. Okay. So I've just kind of rotated them a little bit. You kind of just notice everybody just rotated like one spot to the left. Nothing else really changes. So for carbon number 4, if I work the rest of my way up, okay, so this is carbon 6, this is carbon 5, 4, 3, 2, and 1. Okay, nothing else changes. So the OH that was on carbon 4 stays here, the H stays here. Doesn't look like an H, it looks like an A. Okay, on carbon number 3, there's an H, and then there's an OH. On carbon number 2, there's an OH, and then there's an H. Now, carbon number 1 does change a little bit as well. Okay, what ends up happening is this O at the bottom interacts with the group that is there with the carbon that makes up the aldehyde. So carbon number 1 changes as well, and it changes into something like this. The H stays where it is, Okay, but the double bonded O ends up turning in to an OH. Okay, and it will change in just a second. I'm going to leave it like that for the moment. Okay. And then what takes place here is this OH kind of comes up here and interacts with the carbon. Okay. And it ends up turning into an oxygen. Okay. And water, in essence, is basically lost. So what this turns into, okay, this O turns into an OH. Okay, nothing else here is changing, right? This was an OH, this is an H. Okay, and this had already changed. We're going to change this directly to an O and connect it right there. This H stays where it is, and then the CH2OH stays where it is as well. Okay. Now, this still doesn't look at all like the picture above. Okay. Because we're not quite there. So, everything that's over here on this side is going to end up above the ring in our diagram, and everything that's over here ends up below our ring in our diagram. Okay, so what I'm going to kind of do is I'm going to go through and again kind of relabel all of my carbons. Carbon 1, carbon 2, 3, 4, 5, and 6. I'm also going to label these carbons in my diagram up here. Okay. This is carbon 1, carbon 2, carbon 3, 4, 5, and 6. Okay. What I would like you to notice is what's happened. This O is this O here. Okay. Everything that's on the right side is found below the ring, so it's shown on the bottom. So the OH from carbon number 1, the OH from carbon number 2, the H from carbon number 3, the OH from carbon number 4, and the H from carbon number 5. Everything that's on the left is above the ring. So this H is here, then the H, the OH, the H, and the C2OH. And we have completed our structure. We know that this is alpha because of the OH here. Okay. The only change that occurs for the beta, 100% only change that changes, okay, is right here. Okay, that's the only change for beta versus alpha. The OH and the H switch places. Okay, I would like to attempt to give you a chance to try to create this. So I would kind of like you to take it from here, okay, from the beginning, and try your best to turn it into this, and then we'll go over it. So if you could pause the video to try to turn your structure glucose, the straight form structure, into the Haworth projection, that would rock. I'm going to recommend that you pause the video now, and then we'll go over it. Okay, so I'm kind of hoping your initial diagram looks similar to mine here. Again, the rotation still occurs. The CH2OH goes to the left, the H goes to the right there a little bit. Okay, so they go in a clockwise formation. The O connects in the same spot. The only difference was that the change occurred here. The OH is on the other side. You'll notice that sometimes I draw it OH like HO, and sometimes I draw it OH. Does not matter to me which way you draw it, honestly. Okay, and then again, everything that is on the left side is above in the ring, and everything that's on the right side is below in the ring. So the only change that should have occurred was right here to make the beta glucose. Okay, and again, this is definitely something I think we're going to need to kind of go over a little bit more together. I did post another video on Fischer projections and Hayward's projections from Khan Academy that should also help. I just kind of wanted you guys to get a basic idea of this through the videos before we talk about them together. Okay. The rest of the PowerPoint should not take us all that long to run through. It's a lot of just basic information on important monosaccharides and disaccharides and polysaccharides. Here we go. All right, so some important monosaccharides. Fructose, it's the sweetest of all sugars. It's found in corn syrup and honey. It is a ketohexose, okay? You can see that I have the Hayward projection as well as the straight form Fischer-like projection for both of those, okay? Then we have galactose. It's a component of lactose. It's a component of the principal sugar found in milk. It's an autohexose. It is extremely similar. It's a derivative of glucose. Okay, the only change really is over here. In glucose, the OH is on the bottom and the H is on top at that point. That's the only major difference between glucose and galactose. Okay. In addition, we have ribose and deoxyribose. They're found in RNA and DNA and some coenzymes. Okay, there are 5 carbon sugars. What I would like you to kind of notice is that the deoxyribose has an H here, and the ribose has an OH. Okay, that's really it for those for right now. All right, let's talk about some disaccharides. Okay, disaccharides have glycosidic bonds. I think that's how you say that. They're non-specific bonds. They occur between a hemiacetal and any hydroxyl group in a monosaccharide. Okay, they are catalyzed by enzymes, and there's a specific synthesis that goes with this that you guys do not need to know. Okay, the one major sugar that I put here on this slide is maltose. It is a linkage between 2 glucose molecules. Okay, malt sugar is an intermediate in starch hydrolysis. Okay, and we have a C1 hydroxyl that is attached to a C4 of the other molecule. Okay, you can see that here in the diagram. Okay, and really this can be either an alpha or a beta based linkage. It really kind of depends on, you know, the types of sugars that you have when you are creating it. Okay, what you can see here in this example, all right, this OH is below. Okay, so since the OH is below, that's an alpha. And then this other side, okay, the ones that are combining, you still look over here, this could be alpha or beta. Okay, not super important. I just wanted to give you guys an idea of some other disaccharides that exist. All right. Lactose is another disaccharide. Okay. Lactose is milk sugar. It is composed of galactose and glucose. It is a beta 1,4 linkage. Okay, beta galactose interacts with the glucose, and it ends up forming a beta linkage. Okay, you can kind of see that this one's slightly different than the previous slide. The oxygen here appears really to be more above, okay, as opposed to below, like it was in the previous example with maltose. Okay. Finally, we have sucrose. It's table sugar or cane sugar. It's an important carbohydrate in plants. It cannot be created or synthesized by animals. It does not have a linear form. Okay, this is going to kind of be important when we get into some of the labs, but because it doesn't have a linear form, it cannot be reduced. Okay, so it's a sugar that cannot be reduced. Okay. When you think of reduction, of course, remember that oxidation reduction is based on hydrogens. Okay. So there is no linear form of sucrose, and so therefore it cannot, exchange hydrogens in any way. All right. Can't gain them or lose them, actually. All right. So the type of linkage that exists for sucrose is an alpha-1 beta-2 linkage. Okay. It is a connection between the first OH group, the alpha-1 on glucose, and the second carbon OH group on the fructose. Okay, again, not super important. Sometimes when it comes to testing, I like to ask you the types of linkages that exist between the sugars. So it's not a bad idea kind of just to make note of those. Okay. Finally, we have polysaccharides. Okay. And polysaccharides, here are some pictures of some, means more than one sugar unit, many more than one. All right. And they can be Homo Polysaccharides or hetero, just like homogeneous and heterogeneous. All right. If they are Homo Polysaccharides, they are made of one type of monosaccharide, right? That makes sense. And then if they are hetero, okay, they're made of at least two different types of monosaccharides. Okay. So we're going to just kind of run through a little bit about each type. Okay. And again, I like to ask some basic questions on the test related to how these are different. So first things first, they are all three that we're going to talk about are Homo Polysaccharides. Okay. So starch is a Homo Polysaccharide. Glycogen is a Homo Polysaccharide. And so is cellulose on the next slide. Okay, starch is for plants, and it's how plants store glucose. Okay, they're composed of two forms of glucose, amylose and amylopectin, I think is how you say that. All right. They contain an alpha-1,6 linkage and an alpha-1,4 linkage. Okay, I'm going to kind of scroll to the top here. And you can see it in this picture as well. You'll notice that the amylopectin has branches, right, up here. And your amylose is linear and straight. Okay. You can also kind of see it here. It's based on the types of linkages that exist between them. Okay. Glycogen, all right, is how animals store glucose. So that's a big difference there. All right. Glycogen in general is extremely similar to our amylopectin, just tends to have shorter branches. And then the linkages that it contains are an alpha-1,4 and an alpha-1,6 linkage. Okay, very similar to that of starch. Okay. So really, animals have glycogen and plants use starch. Okay. The major difference with the starch is that the amylose, so the straighter chains, even, because the types of linkages are very similar. Plants can only have one type and animals can only have the other type. Okay. And finally, we have cellulose, which is our last slide here. It's a final polysaccharide we're going to talk about. It is also a Homo Polysaccharide. Okay, it is the most abundant organic molecule in the world. Okay, and it is a combination of beta glucose units linked by beta bonds. Okay, they're beta-1,4 linkages. It is the structural component in the plant cell wall. Okay, and it cannot be digested by humans. All right. So the huge difference and the major difference between cellulose and starch, okay, is the linkage that exists. All right. So starch has alpha linkages and cellulose has beta linkages. Okay. In our bodies, humans, okay, and most animals, all right, obviously because animals don't do well with cellulose as often either, a little bit better than us sometimes, but humans only have the enzyme for alpha linkage breakdown. So humans only have the enzyme for alpha linkages. So humans have the enzyme to break down the alpha linkages. Hence why we can break starch down, but we do not have the enzyme for beta. So no enzyme for beta linkages. Okay. And because of that, we cannot break cellulose down within our bodies. All right, and that concludes our study on Chapter 16.